We're going to do something new in this video. So I'm going to want you to try the activities in the PDF file called Introduction to Integer Multiples and Exponents. That'll give you an idea of the type of concepts that we're going to be working on in this next investigation. Okay, so specifically we're going to be talking about integer multiples in rings. We're going to introduce the idea of multiplying an element of a ring by an integer. I have multiplying in quotes because it's not going to be ring multiplication. We're going to define precisely what it means to multiply an element of a ring by a natural number. Eventually we'll get to all integers, but right now we're going to concentrate on natural numbers. And then we're going to prove a theorem using that definition. Okay, so here's the question that kind of motivates everything that we're going to be doing here. So if R is a ring, and if X is an element of that ring, what does it mean to multiply that element in the ring X by 4? Now this may seem like a strange question because X is a ring element, 4 is an integer, and so in some sense we shouldn't be able to multiply them at all. They're not part of the multiplication in the ring. However, the way we think about multiplication by 4 is usually some kind of repeated addition. So we might think it's, oh yeah, x plus x plus x plus x. That's something that makes sense in the ring because that's just ring addition, and the 4 just tells us how many times to add the x together. Of course, if you look at that too closely, you can say, well, addition is a binary operation, not an operation among 4 elements. So technically, if you want to be really picky about it, that expression doesn't make sense. But we've gotten around that situation before by just adding parentheses appropriately. So if we add it like this, then we take those first two x's, add them together, take that element, add x to it again, and then take that element and add x to it again. So each time we're adding two elements together, it's just that we have to do it multiple times. Of course, that's not the only way that we can add parentheses. We can do it this way. So we can add the first two, then the last two, and then whatever those outcomes are, we add those together. And of course, that's not the only way either. We can do it that way too. You're getting the idea. There are lots of different ways we can do the parentheses, which begs the question, well, which of those is correct? And of course, because of the associative property, well, they're all correct, right? They're all equal by the associative property, so any one of those can count as multiplying x by 4. All right, so that tells us that if we want to think about multiplying a ring element by an integer, it might make sense to approach this as a recursive definition. So again, here's how recursion works. I'm going to show you on the first couple iterations just so you can see how it works. If we want to do 2 times x, well, we of course think of that as x plus x. If we do 3 times x, well, we could think of it as x plus x and add parentheses, but we could also think about it is if we're adding 3 x's, those first 2 x's are just 2 times x, which we just computed in the previous line, so we can think of 3 times x as 2x plus x. Right? And once we know what 3x is, if we want to know what 4x is, well, again, we're adding 4 x's, but if we think of adding the first 3 x's, that's 3x, which is what we just computed in the previous line, so we could just think of that as 3x plus x. As you can see, every time we compute one of these, we can compute the next one using the one we just computed. And we keep on going in that way. And whenever doing something like that, that's what's called a recursive definition. So if R is a ring, and if x is an element of R, and if n is a natural number, we can define n times x in the following way. So the way we do this recursively is we first have to explicitly define the first one. So for n equals 1, we have 1 times x equal x. We just leave that one alone. And then for the n greater than 1, we use the previous one that we just did to define it. So if you want to find n times x for n greater than 1, that's going to be n minus 1x, that's the previous one that we just did, plus x. So for example, if I want to know what 4x is, by the recursive definition, since it's greater than 1, we get 3x plus x. Now 3x is going to be 2x plus x, so we can substitute that in by the recursive definition. That 2x by the recursive definition again is going to be x plus x, and there we have our element. All right, so now we're going to try to prove a theorem. It may be a theorem that looks obvious, but if you look closely enough, you can see why it needs proving. So if R is a ring, and if X and Y are ring elements, and if N is a natural number, then N times the quantity X plus Y is equal to NX plus NY. Now, if you're not looking at that too carefully, you might think, well, gosh, that's just the associative property for rings. Except it is not the distributive property for rings. In order to use the distributive property for rings, you need all the things that you're multiplying to be elements in R. And if you look closely, X is an element of R, Y is an element of R, but N is decidedly not an element of R. N is a natural number. So technically speaking, this is not the distributive property, which means that it needs to be proven. But that's okay. We got a nice recursive definition for multiplying by integers. We should be able to prove this by induction. Not as always, but as often is the case, whenever we do induction, it might help to do a couple of example induction steps so you can see how it's going to work in the general case. So if I want to do 1 times x plus y, and if I want to prove that is equal to 1 times x plus 1 times y, well, by the definition of integer multiplication by 1 times x plus y is just x plus y. And also, by the same definition of integer multiplication, x is equal to 1 times x, y is equal to 1 times y. So we get 1 times x plus y equal to 1x plus 1y, which is exactly what we wanted to prove for n equals 1. What about for n equals 2? Well, by the definition of what multiplying by 2 means is, it is the previous 1 times x plus y plus another x plus y. Anytime you multiply something by 2, it's the same as multiplying it by 1 and then adding another copy to it. And that's exactly what we did. In this case, we were adding the copy of x plus y. Well, we just proved what 1 times x plus y was. 1 times x plus y in the previous line is 1x plus 1y, so we can substitute that in. And then, of course, we leave the plus x plus y alone. And now I'm going to use the associative property and the commutative property to put all the x's together and put all the y's together. And very conveniently, 1x plus x, that may look familiar, that's exactly the definition of 2 times x. And 1y plus y, that's exactly the definition of 2 times y. That's the definition of multiplication by a natural number. And that's exactly what we wanted to prove. 2 times x plus y is equal to 2x plus 2y. Let's do it one more time just to make sure we've got the hang of it. If I want to do 3 times x plus y, well, 3 times anything is 2 times that thing plus that thing again. So that's 2 times x plus y again. By the computation we just did, 2 times x plus y is equal to 2x plus 2y. We leave the other x plus y alone. We use the associative property and a commutative property again together to put the x's together and the y's together. And then by the definition of multiplication by 3 times x is equal to 2x plus x. That's the first one. 3 times y is equal to 2 times 2y plus y. That's going to be the second one. And again, we get 3 times x plus y equal to 3x plus 3y. So you can see how this inductive step is going to work. And the very top line of that shows us how the base case is going to work. All right, so let's see if we can do this proof. As mentioned before, and as is almost always the case when you're using recursive definitions, we're going to do a proof by induction. So for our base case, we got to start with n equals 1. So for n equals 1, we want to know what 1 times x plus y is. But 1 times anything, by the definition of multiplication by natural numbers, is itself, right? So 1 times x plus y is equal to x plus y. But x is equal to 1 times x, y is equal to 1 times y. And so we get 1 times x plus 1 times y. And that's our base case, just like we did in the previous slide. For the inductive step, I'm going to state carefully what we're going to assume, what we have to prove. We're going to assume that n times x plus y is equal to nx plus ny. And we're going to show that n plus 1 times x plus y is equal to n plus 1 times x plus n plus 1 times y. All right, so let's see if we can figure out what n plus 1 times x plus y is. Well, by the recursive definition of multiplication by an integer, n plus 1 times x times anything is n times that something plus that something again, right? Because n plus 1, the one right before it is n. So we get n times x plus y again. Now, by induction, remember, we're assuming that n times x plus y is equal to nx plus ny. So let's go ahead and replace it with that. Oops, sorry. That first line came from the definition of integer multiplication. Now we're going to apply the induction hypothesis to n times x plus y. We get nx plus ny. And again, this is by the induction hypothesis. Now we're going to use the commutative and associative properties to combine the x's and combine the y's. We get nx plus x plus ny plus y. And of course, that is by the associative and commutative properties. And then we're going to use the definition of multiplication by n plus 1. N plus 1 times anything is n times that something plus the something again. So nx plus x, working that backwards, is n plus 1 times x. Ny plus y is n plus 1 times y. And again, that's the definition of integer multiplication. And that's what we were trying to prove. All right, so now I think you're ready for the activities for integer multiples, natural numbers. That's the name of the PDF file that you'll find right next to this video.